very important insights about variable elimination and how to best pick the elimination ordering is provided by thinking about the operations that variable elimination executes as operations on a graph. So let's see what that does. So let's consider the initial graph in our example, and let's first view this graph in terms of the factors that it involves. So if this is the set of factors that we have in our analysis, viewed as undirected, viewed as simply as factors. So what is the structure of the graph that corresponds to this set of factors? Well, first we're going to make all of the edges undirected, but that's not enough because we see, for example, that we have a factor here, which is a factor over g, I, and d. And so what we need to do is we need to add an edge between I and d to represent the fact that they're together in a factor. Other examples, other cases where we need to do this correspond to the other V structures that we have in this graph. So here, for example, we have a V structure involving J, so we're going to need to connect J's two parents, and similarly for H's two parents. This step, by the way, is called, not by me, moralization, because of the dubious moral value of marrying the parents of a child, no matter how many of them there are. And so I did not invent that name. So having moralized the graph, we now have this version of it. And this is what we previously defined to be the induced Markov network for the current set of factors. So now let's think about a variable elimination step and what it does to this graph. So let's begin by eliminating C, and if you remember, that involved this operation. And so first, eliminating C is changing the set of factors. It removes these two factors over here from the set and introduces a new factor, tau 1 of d. So the induced graph is now going to look like the following. We've taken C out, and the remainder is the induced graph over the set of factors. Okay? Now we're going to continue. We're going to eliminate d. So once again, we're going to take the two factors that we've now introduced, these two factors that are involved here, which is tau 1 of d and phi g of gi and d, going to multiply them and going to eliminate d. And so the resulting, graph is now going to look like this. Where again, the nodes with the dashed edges are not really there. They're just there to remind us that they were there before. Continuing on, we're going to eliminate I, and that involves multiplying in this term, and this term. And now something interesting is going to happen. the factor that we introduced, which is tau 3 of S and G, is a factor that doesn't have an edge in the current graph. So if we're interested in having this graph represent our current set of factors, we're going to need to introduce this edge between G and S, because that edge is necessary because S and G are together in the same factor. So that edge is called a fill edge. It's an edge that I had to introduce because of the elimination ordering. So one way to think about this is using the following example. Imagine that every variable that's eliminated is going off on a trip around the world. And when it's doing that, it's throwing a big goodbye bash and inviting all of its friends to come and join it. And when it does that, all of its friends get to meet each other and say, oh, you guys are nice. I'm going to be your friends too. And so all of the friends of the variable that's eliminated become friends as a consequence of the elimination step. Okay? So let me write that down. All variables connected to, in this case, I, become connected after it's eliminated. So become connected directly. And that's a general consequence of the elimination step process. It's just that the previous ones didn't happen to introduce fill edges. Okay, let's continue. So now we're going to eliminate H. H also doesn't introduce any fill edges, and so we're going to end up with that. And basically the remaining steps are pretty mundane. We're going to eliminate G, L, and S, and we're going to end up with the following graph. So this particular variable elimination process only introduced one fill edge, which is a fairly conservative thing, and shows that we selected a pretty good elimination ordering in this case. So we can now take and put all of these edges that we ended up using together in a single graph, and that graph is called the induced graph. And the induced graph, which is denoted I for induced, phi comma alpha, over a set of factors phi, and induced by particular ordering alpha, because you remember that we were getting different complexities and we're going to have different fill edges depending on the order in which variables are eliminated. So this induced graph has the following properties. It's an undirected graph where we connect every pair of variables xi and xj if they ever appeared in the same factor when we ran variable elimination using alpha as the ordering. And so in this case, all of the black edges were there to begin with, and we ended up introducing just one of those additional new or fill edges. So now there's some interesting properties of the induced graph that are worth noting. First of all, there's properties that relate factors produced during variable elimination and cliques in the induced graph. So first of all, let's define what a clique is. A clique is a maximal fully connected subgraph. So let's parse that too. So for example, DIG here is a fully connected subgraph because all of its three nodes are connected to each other. And it's maximal because I can't add any other variable to this and still have that property hold. So if I try and add S, for example, then S is not connected to D. If I try and add C, C is not connected to I or G. So I can't add any other variable to this particular clique. So it's a clique. Here is a clique that's not maximal. So so it's not a clique. So GLJ is a fully connected subgraph, but it's not maximal because I can add S and still have that hold. So here is another clique in this graph. So we have GID being one clique, GS, L, and J being another clique. We're going to have a third one, which is G, S, and I. Another one, which is CD. And let's see if I have enough colors to do this. And a final one, which is G, H, and J. And if we now look at the factors that we produced in the course of variable elimination, we see that there is an exact correspondence between the factors and those cliques. So here, for example, the yellow one is CD, which is this one over here. This one over here, which is GID, is the red one, this one. So that's the red one. This one has SIG, so that's the green one, this one. This one is HGJ, which is the brown one. Tau 5 induces the big factor, the one that involves 4 variables, and that's the blue factor over GS, L, and J. And this one doesn't actually introduce any new cliques, which is why it doesn't have any cliques associated with it. So every factor produced during variable elimination is a clique in the induced graph. Okay. We can equally well check, and we saw that in the previous slide already, that every maximal clique in the induced graph is a factor that's produced during variable elimination. So we've demonstrated this to ourselves by inspection, but let's actually do a proof of this. So let's consider a maximal clique in this induced graph. So let's consider, for example, GS, L, and J. So that's a maximal clique. And now let's consider the run of variable elimination. And one of those variables has to be, the one to be eliminated first. So some variable in this clique is first to be eliminated. Well, what happens when a variable is eliminated? Once it's eliminated, it doesn't have any more edges that get added to it. So once a variable is eliminated, it has no new neighbors are added to it. Which means that at the time that it was eliminated, it had all the neighbors that it had in the clique. All the clique members as neighbors. But if that's the case, then it means that it had factors involving all of those other guys. So it participated in factors with all these other guys. And that means that when I multiply them all together, we're going to end up with a factor over all of them. And that is a proof that every maximal clique in the induced graph must correspond to a factor produced during the variable elimination algorithm. So now that we've constructed a graphical view of variable elimination, we can go ahead and construct a measure of the complexity of variable elimination. And that is a measure known as the induced width. So first, we're going to define the width of an induced graph is the number of nodes in the largest clique in the graph by convention minus 1. Why minus 1? No good reason, but that's what people, that's the definition of induced width. The minimal induced width of the graph is the minimum over all possible elimination orderings alpha of the width of the induced graph. So this is the best achievable complexity that one can aspire to with any elimination ordering. You can think of the minimal induced width of the graph as a lower bound on the best performance of variable elimination for any model that factorizes over the graph K. In summary, we've seen that the variable elimination algorithm can be viewed quite intuitively as taking a set of steps, each of which transforms the graph. Specifically, a variable elimination step for a variable x takes all of x's neighbors that may or may not have been connected before and connects them to each other. The result of all this is something called the induced graph, and we've seen that the induced graph is possibly quite connected as a result of this variable elimination process, and that the cliques in this induced graph, that is the maximally connected subsets, maximally fully connected subsets, correspond directly to the complexity of the variable elimination algorithm, and as we'll see, can therefore help us analyze its computational properties. When we discussed variable elimination, we said that variable elimination is correct no matter the elimination ordering that's used, but we also showed that the elimination ordering can make a very significant difference to the computational complexity of the algorithm. So that begs the question of how we find a good elimination ordering. Fortunately, the computational analysis based on graphs that we recently did gives us an intuition into how to find good elimination orderings, because it turns out that the notion of an induced graph and the way in which it indicates the complexity of variable elimination can allow us to construct good methods for finding elimination orderings with good computational properties. How good of an elimination ordering can we construct? So here is yet another example of the fact that any interesting problem is NP-hard. So the following problem is NP-hard also. For graph H, determining whether there exists any elimination ordering alpha for which the induced width is less than or equal to some fixed value k, that problem is NP-complete. So you might say to yourself, well, that's not surprising. I mean, probabilistic inference is NP-complete, so obviously finding a really good elimination ordering is going to be NP-complete. Turns out that this is a separate NP hardness problem. That is, even if you could solve this problem, even if somebody gave you the best elimination ordering, you're still going to have graphs for which the width is sufficiently large so that you can't actually solve the problem in polynomial time. So finding the best induced width, the elimination ordering that gives you the best induced width does not give you polynomial time performance in general. And so these are two separate NP-hard problems. So how do you find a good elimination ordering? Fortunately, simple heuristics actually do pretty well. So one standard way of finding good elimination ordering is to simply do a greedy search, eliminating one variable at a time, where at each point in the elimination, you use some kind of heuristic cost function to decide which variable you're going to eliminate next. And there's some obvious cost functions to use, and it turns out that surprisingly they work pretty well. So, for example, one cost function is what's called min neighbors, which is to pick the node that has the minimal number of neighbors in the current graph. So you want to pick the variable that's connected to the fewest friends so that it has the smallest party or produces the smallest factor. So this corresponds to the smallest factor, or the one whose cardinality is smallest in terms of number of variables. Min weight accounts for the fact that sometimes you have variables that have 100 values and others that have 2 values. And if you just count variables, you're going to ignore that distinction. So min weight computes the weight, or the total number of values in the factor formed. So min weight is a way of capturing the fact that if you have 2 variables, each of which has 100 values, you might prefer to nevertheless pick a factor that has 5 variables, each of which has only 2 values. So these just look at the size of the factors formed, and they ignore the fact that some of these factors might be inevitable. So a different strategy is to look at how much extra work is caused by the elimination ordering. So min-fill is a strategy that says, if I eliminate this node, how many nodes that weren't friends before become friends due to this elimination step? So here, basically, I'm counting added complexity above and beyond the complexity that I would have had from the edges that I previously generated. And finally, again, you have a weighted version of the fill heuristic that takes into account not just the number of edges, but also how heavy they are. That is, how big are the, what's the domain size of the variables that they connect. And it turns out that min-fill, which is actually quite often used in practice, is a pretty good heuristic. Now, one important way of understanding the issues of finding elimination orderings is by looking at the following result. And the result tells us that the induced graph that is produced by variable elimination, regardless of the elimination ordering, is triangulated. Now, what does triangulated mean? Triangulated means that you cannot have a loop of size more than 3 that doesn't have a bridge, an edge that goes in one direction or another, so that there's a way of crossing across that loop without going all the way around. Let's convince ourselves that this is true. So here's a simple proof. So once again, consider a set of variables and assume by contradiction that there is a loop like this. So for example, assume that we have a loop of size greater than 3. And again, one of these variables has to be the first to be eliminated. So assume that C is first to be eliminated. Well, once we eliminate C, we end up introducing an edge between B and D. And so there has to be an edge between those 2 neighbors of C. Because when C is eliminated, the CD edge must exist. The CB edge must exist, because as we've observed before, you don't add any neighbors to C once you eliminate it. And so at that point, a fill edge must be added. So it turns out that one way to find an elimination ordering, an alternative to the heuristic that I mentioned earlier, is to find a low-width triangulation of the original graph. And there's been a lot of work in the graph theory literature on triangulating graphs, which we're not going to talk about, but it turns out that you could use all of that literature for finding good low-width triangulations and then use that for constructing an elimination ordering. So now let's convince ourselves that this can make a big difference. So let's consider a practical application. And this is an application to robot localization and mapping. So what we're going to see here is a robot moving around, and at each point in time, it sees several landmarks, and it knows which landmarks it sees. It can recognize them. And what it senses at each point is some kind of approximate distance to the closest landmark. So let's write that down as a graphical model. The graphical model looks something like this. We have at each point in time a robot pose, which is the robot pose at time 0, 1, up to the end of the trajectory, t. And we have a set of landmarks whose positions are fixed. The landmarks don't move. So notice that these are not random variables that change over time. They're just there, and they're constant. And what you see here in gray are the observations. So this, for example, assumes that at time 1, robot saw landmark 1. And so what we have here is the observation. The observed distance is a function of the robot pose and the landmark position. And here at time 2, we have that the robot saw landmark 2. So we have this dependency over here. And at time 3, the robot also saw landmark 2. So you have 2 observations for the same landmark. In here, I didn't draw the fact that you could actually see the same landmark. You can see more than one landmark at a given point in time, but that also is easy to add in. Okay, so now if we take the previous robot trajectory that we saw and we write down the Markov network that represents the factors, we see that we have these light blue little dots that represent the robot pose at every point in time. We see that we have these temporal persistence edges that represent the fact that the robot pose at time t is correlated with its position at time t plus 1. And we have these dark blue robot pose variables these dark blue landmark position variables, where we see that a landmark is connected to all of the positions at which it was visible by the robot. And this is an edge that's induced by the V structure that we have over here. So this is an edge that's induced by this V structure, which we have because Z1's been observed. Okay, so does elimination ordering matter? Oh boy. This is what you get when you eliminate the robot poses first and then the landmark. And this, what you see here, is the induced graph. And you can see that you get this huge spaghetti where most of the landmarks are connected to all other landmarks. Okay, what about a different elimination ordering? This one's already better. This is what happens when you eliminate landmarks and then poses. And you see the induced graph that you get over poses, and you can see that it's still pretty densely connected, but it's not nearly as bad as the spaghetti that we had before. And finally, let's look at the result of min-fill elimination. So this is what you're seeing is the fill edges being constructed. And you can see that it's actually very sparse. Let's look at it again. Very few fill edges are actually added over the course of the trajectory. And so the elimination ordering makes a very big difference. In summary, we've seen that finding the optimal elimination ordering is an NP-hard problem, and that it is an NP-hardness that is different from the intrinsic difficulty of inferencing graphical models. However, we've also shown that the graph-based view of variable elimination gives us a set of very simple and intuitive heuristics that allow us to construct good elimination orderings. And those work by looking at the induced graph as it's constructed in the course of variable elimination and trying to keep it small and sparse. These heuristics, although simple and certainly potentially not providing not good performance in the worst case, are often quite reasonable in practice and are very commonly used.